Okay, so our next topic is measuring temperature in our heat and temperature unit. So what is temperature? So temperature is basically how warm or cool things are. And we can estimate temperature by touching, which has been, it's still done today. It was done in the past. So we have these nerve endings in the human skin, which are sensitive to different temperatures. So people, they basically can learn to recognize the feeling of particular temperatures just by experiencing those. So for example, touching a person's forehead with the back of the hand to see if they have a fever. Another example is our welders and glass blowers. They can estimate when a flame is hot enough to soften the metal or the glass. They can look at like the color of the flame. Another example, people working with hot glowing materials, they can estimate the temperature of materials again by the color of the light that they're giving off. Another example is astronomers. They can judge the temperature of stars by the color of the light that they're emitting. Okay, but estimating with your eyes or your skin, it's not always the safest or the most reliable. All right, so we have this give it a try activity in the textbook. Just gonna. All right, so we have these devices called thermometers. Thermometers, they are mechanical or electrical devices for measuring temperature. First constructed by the Italian scientist Galileo in the early 17th century. So in 3.4a, we can see the figure here. Galileo invented his air thermometer around 1600. So as the air in the upper bulb cooled or warmed, a bubble of liquid will move up or down in the tube. 100 years later, the design was improved, shown in this figure here. This is a more portable thermometer. It's a liquid thermometer that was invented around 1700. You put a liquid in the bulb and part way up the stem, and then you'll see a movement happening there. So temperature scales. These are the scales that you see, for example, on a thermometer. So it's a series of equally divided sections that are marked and numbered for use in measurement. So the Celsius scale, this is the commonly used scale in Canada and many other countries. So Anders Celsius, he was alive 1701 to 1744, and he used the degree as the unit of temperature. And he based his standards for comparison on the properties of water. So what he did was he assigned 0 degrees to the temperature at which ice melts at sea level, and then he assigned 100 degrees to the temperature at which water boils at sea level. And then he evenly spaced the region between 0 and 100. One thing to note about water and why sea level is mentioned is because water boils at lower temperatures the farther above sea level you go. So if you're up in the mountains, it would take less time to heat up water, to boil water. It would take less time to make a mug of hot chocolate, for example, on top of a mountain. Compare that to the Mount Everest. At the top of Mount Everest, water would boil at only 69 degrees Celsius. So the two fixed temperatures that we mentioned, so 0 degrees Celsius for freezing water and 100 degrees Celsius for boiling water, and those are used for calibrating thermometers. And again, we talked about sea level. Calibration, it should be done at sea level using very pure water because again, salt water is different. It doesn't freeze until it is colder than 0 degrees Celsius. Another factor is pressure. Pressure also affects the boiling point and freezing point of water. High pressures will cause ice to flow or melt at temperatures below 0 degrees Celsius. And under low pressure, water will start boiling before it reaches 100 degrees Celsius. In Alberta, we're at a high altitude. It means the weight of the water above is smaller than it would be at sea level. So water starts to boil at several degrees less than 100 degrees Celsius. This image is just showing, again, temperature scales and calibration. So the first thing that's done is the liquid level in an ice water bath, you mark that at 0 degrees Celsius as shown here, from here. Step 2, put it into boiling water and you would mark it as 100 degrees Celsius. And then you have your 100 degrees Celsius and 0 degrees Celsius here, and then you're going to evenly divide between the 0 and the 100 degrees Celsius. All right, so the scale is divided into 100 equal degrees and numbered. Kelvin scale, this is something that was required by scientists. They needed a temperature scale that started at the coldest possible temperature, which is at absolute 0. So this scale was named the Kelvin scale in honor of William Thomson. He was given the title Lord Kelvin. So scientists predict that absolute 0, the coldest possible temperature, is negative 273.15 degrees Celsius. So if we see here, that's shown as 0 Kelvin, and shown here in Celsius at negative 273.15 degrees Celsius. And they're not called degrees, they're just called kelvins. So the freezing temperature of water at sea level is 273.15 kelvins. So at 0 degrees Celsius, we have 273.15 Kelvin, and at 0 Kelvin here we have negative 273.15 degrees Celsius. This is similar to the investigation we've already done. I believe it is the exact same investigation that we just finished last class, the boiling hot, freezing cold investigation. Just keep in mind, they're not matched here. That's what you guys did for homework already. All right, the right device for the job. So thermometers are developed to suit a purpose. We wouldn't use the same device to measure body temperature and use that same device to measure the temperature of the sun. All right, so different devices, right, for what you're trying to measure. So when we look at these devices, there's something in there called a sensor. This is a material which is affected by changes in some feature of the environment, so such as the temperature. Then there is a signal. The sensor will produce a signal, information about the temperature. It might be as an electrical current. And then there's a responder. The signal affects a responder, for example, a pointer, light, or other mechanism that uses the signal in some way. So for example, we'll talk about the thermocouple. So in a thermocouple, we have wires that are made of 2 different metals, and those are twisted together. And then the wire tips are heated, and a small electric current is generated. And the amount of current depends on the temperature of the wires. The electrical current can be used to turn a switch or a valve on or off if the temperature changes. So this can measure temperatures higher than ordinary thermometers. Not good for using, or not very good at measuring low temperatures accurately. So let's take a look here at some examples here of a thermocouple. So again, we have 2 wires twisted together. So for example, in this one here, we have an iron wire and a copper wire. All right, so here it's being used to measure the temperature of a liquid. And then here we have another one here. We have like candle. We have 2 types of wires. It's saying it's a copper lead wire. No, wire type A, wire type B is not really told what the wires are made of. But here we can see the 2 types of wires. One was iron and one was copper. All right, another example, the bimetallic strip. Again, it's made of 2 different metals that are joined firmly together. The strip gets heated. One metal will expand more than the other. The strip is forced to coil more tightly, and then when the strip cools, the process is reversed. So basically the same metal that expanded rapidly will now contract rapidly, and the strip uncoils again. The movements of the strip, they operate a type of electrical switch, and this is used to control furnaces, air conditioners, as well as refrigerators. So here we can see what's happening. We have a bimetallic strip in a thermostat. So in a thermostat, the bimetallic strip is fastened to a glass capsule, and it's got a drop of mercury inside of it. And when the bimetallic strip cools, the capsule will tilt. The mercury is going to roll to one end, filling the gap between the two wires, and it'll complete an electrical circuit. So for example, the furnace or the air conditioner will be switched on. When the bimetallic strip bends the other way, the mercury will roll away from the wires. It'll break the circuit, and therefore the furnace or the air conditioner will be switched off. All right. So in this case, the bimetallic strip copper was made of copper and iron. Again, just showing the bimetallic strip and how it works. So when heated, the copper expands more than iron. That will make the strip bend. All right, so here it's showing on, and then it turns off as it bends. So thermal circuit breakers, they trip and turn off the circuit if the current is too great. They work because the current heats up a bimetallic strip. The bimetallic strip will bend, and this movement will switch off the circuit. All right, next is the body. So we talked about this a little bit, but there is a temperature sensor inside the brain, and it monitors our internal temperature. So if the temperature outside the body changes, the sensor will signal the brain to release chemicals that will enable the body to adjust to its normal body temperature of about 37 degrees Celsius. All right, so this is just showing what's happening to the body and the brain. So here, for example, the stimulus, there's an increased body temperature. So for example, if you're exercising or the climate is hot, so in the brain, there's an activation in the brain, and what will happen is, for example, the skin, blood vessels, they'll dilate, so heat can radiate from the skin surface. Sweat glands will get activated, so you start sweating, perspiration, that'll vaporize by body heat to help to cool down the body. And then here, if there's a decreased temperature, maybe a cold environment, so maybe it's cold outside, so again, it'll get activated in the brain. In the skin, the blood vessels will constrict. So blood gets diverted from the skin to deeper tissues. It's going to minimize heat loss from the skin surface. Shivering will begin. So skeletal muscles get activated and you'll start to shiver, and that'll generate heat as well. All right, so the body is trying to get back to the 37 degrees Celsius. This here is a recording thermometer. It's also called a thermograph. So again, it contains a bimetallic strip. It'll coil and uncoil as the temperature changes. One end is attached to a lever that holds a special pen. There's the bimetallic strip there. There's the pen. So tiny movements of the bimetallic strip will cause these larger movements of the pen, and then it'll trace a line on this paper here that's attached to a slowly turning drum. So the drum usually makes one turn every 7 days. All right, this is an infrared thermogram. So anything that is warmer than absolute zero, it gives off infrared radiation, which is also called IR for infrared radiation. So it's a type of radiation that the eyes cannot detect. Skin can detect IR when we're near hot objects. It can be photographed with special films or detected by electronic sensors that will then display the images. The color or brightness of the infrared image shows the temperature of the object. So here we have an image on the left. This image is showing an IR image, and the one on the right is just the normal picture of the same image. All right, so we can see like different colors here. And this would be useful For example, in the winter, you could find where maybe air is leaking around doors and windows. You can use the infrared image. All right, and that way you can reduce heating costs and conserve fuel. Here's another infrared thermogram of a dog, and you can see like the temperatures of the different colors, right? So purple down here, it's about 22 degrees Celsius, and then as we get up to red, we're reaching that about 37 degrees Celsius. So what to say? Thermographic image of a dog. The eyes are in general the reference points used to measure the core temperature. So the eyes in that reddish range. The cooling system of the nose, purple. All right, I do have a couple of videos here to show.